Ever get stuck staring at that computer screen just wondering, is this program ever going to finish? Like, is it actually doing anything? Today we're diving into the halting problem.
Yeah, it's a fascinating concept that basically says you can't always know for sure.
Okay, so no more impatient refreshing or forced quitting.
Not exactly, but it does have some pretty real implications for how we write code and even for cybersecurity. I'm intrigued.
It's pretty deep.
So to help us unpack all of this, we've got articles from Wikipedia and Geeks for Geeks, even a Reddit thread with some interesting perspectives. We're going deep on the halting problem, folks. By the end, you'll know what it is and why it matters. Sound good?
Sounds good.
So what exactly is the halting problem?
Well, it all boils down to one question, really.
Okay.
Can you create a program that can analyze any other program and tell you with absolute certainty if it'll eventually stop running? Or will it get stuck in one of those dreaded infinite loops?
It's like a universal code checker. Can we create something that can always predict if a program will ever finish? Exactly. That's the essence of the halting problem. And the answer is, well, you can't. No single algorithm can be created that can solve this problem for every possible program and every possible input you could give it.
Hold on. Why not? It seems like if we were clever enough, we could write a program to analyze any other program.
That's where it gets really interesting. Geeks for Geeks uses a proof by contradiction to explain this, and it's pretty elegant, actually. Let's assume we could create this program. Let's call it the halting machine. It can tell us if any program will ever halt or not.
Okay, so we've got our magical halting machine. What's the contradiction?
Well, think about this. We could then use that very same halting machine to build another program, right? And this new program is designed to do the opposite of whatever the halting machine predicts.
Okay, so it's like a mischievous program. It's going to defy our halting machine.
Right. If the halting machine says a program will stop, this new program we built will make sure it loops forever. And if the halting machine predicts an infinite loop, our program will immediately stop.
So we've essentially created this program that is always going against our halting machine.
Exactly. And here's the kicker. What happens when we feed this mischievous program into the halting machine?
Uh-oh.
Right. If the machine says it will halt, well, the program's designed to run forever, contradiction. And if it predicts an infinite loop, the program will just immediately stop, another contradiction.
So by assuming we can create this halting machine, we end up creating a paradox. It can't exist. That's a pretty neat way to show that.
It is, and Wikipedia actually visualizes this paradox in a really interesting way.
Yeah.
Imagine a giant grid where each row and column represents a different program. And we're trying to build a program that goes down the diagonal of this grid, where a program has to analyze itself to see if each program halts.
Okay, I'm picturing it.
But this inevitably leads to a logical contradiction.
So this is like saying we're trying to create a program to solve this.
Yeah.
And it creates a sort of logical trap that you just can't escape. It's like a computer science version of that. This statement is false paradox.
That's a great analogy.
So, okay, we've got this theoretical problem, but what should I care? Like, does this actually have real world consequences?
Absolutely. That Reddit thread we mentioned has some great examples. Take compiler optimization.
Okay.
So compilers are programs that translate the code you write into something the computer can actually understand, and they try to make your code run faster and more efficiently.
Right. So compilers are like the interpreters between what we write and what the computer can actually process.
Exactly. And now imagine a perfect compiler. It could identify and eliminate all the infinite loops in your code, but because of the halting problem, this is impossible.
So you're saying even with all our fancy algorithms and supercomputers, there are just some things about a program's behavior that are fundamentally unpredictable.
You got it. And it doesn't stop there. Think about cybersecurity.
Okay.
Antivirus software tries to identify and stop malicious code.
Right. It needs to be able to figure out if a program is going to do something harmful.
Right. But figuring out if a program will eventually reach a state where it does something bad, well, proving that is directly tied to the halting problem.
I see.
It's incredibly difficult and sometimes straight up impossible to determine with 100% certainty.
So the halting problem makes it harder to guarantee that antivirus software can catch every single threat. That's a little unsettling.
It is. It even affects something as seemingly straightforward as software testing. You make changes to a program, you want to make sure you didn't introduce new bugs, right?
Right. You don't want your changes to accidentally break something.
Exactly. Part of that is verifying that your modified code stops running under the same conditions as the original code.
So you want to make sure your changes didn't accidentally create some situation where the program can't finish what it's supposed to do.
Exactly. But because of the halting problem, this verification can't always be done perfectly. There's always this possibility of an unforeseen scenario where the code gets stuck.
So even simple things like checking for bugs become way more complex because of the halting problem. This is starting to feel like a pretty big deal. So where do we go from here?
Well, to really appreciate the depth of this, we need to talk about Turing machines.
Turing machines.
Yeah, they're not actual machines, but theoretical models of computation that help us understand what computers can and cannot do.
Okay, so they're like a theoretical blueprint for any computer. Why are they important here?
Because the halting problem was initially proven using this very concept.
Okay, I'm intrigued. What exactly is a Turing machine, and how does it all connect to this?
Let's delve into that fascinating world next time.
Okay, so before we jump down this whole rabbit hole of, compiler optimization and cybersecurity and everything we were talking about Turing machines, I'm ready to hear more about these theoretical blueprints for computers.
All right, well, imagine this. A device with an infinitely long tape.
Infinitely long. Okay.
Yeah, and it's divided into these little cells, and each cell can hold a symbol, kind of like a bit in a computer. And then there's a head that can move back and forth along this tape, reading and writing those symbols.
Okay, I'm picturing like a really, really long ticker tape.
Okay.
And this head is interacting with the symbols on it.
Exactly. And what makes it a Turing machine is a set of instructions that tell that head what to do based on the symbol that it's currently reading. It's like a program for this very simple machine.
So the tape is the memory, the head is kind of like a processor, and the instructions are the software.
You got it. Now here's why this is relevant to the halting problem. Alan Turing, the brilliant mind behind these machines, proved that there's no way to create an algorithm that can determine if any Turing machine will eventually halt or run forever, given a specific input on that tape.
So if I'm understanding this correctly, a Turing machine, as simple as it sounds, can actually model any computation a real computer can do.
That's the remarkable thing. And because the halting problem is undecidable for Turing machines, it means the same problem is undecidable for any computer with equivalent computational power.
Oh, wow. So that means our laptops, smartphones, even supercomputers, they all face this fundamental limitation.
Precisely. And that's why this seemingly abstract concept of the halting problem has such profound implications. It's not just about some theoretical model, it tells us something really fundamental about the nature of computation itself.
So we talked about a few of those implications earlier, like, with compiler optimization and cybersecurity. Can we delve a bit deeper into how the halting problem impacts these areas?
Absolutely. Let's start with compilers. As we discussed, compilers try to optimize your code to make it run faster. One way they do that is by eliminating unnecessary computations like those stuck in those infinite loops.
Right, because an infinite loop is just wasting resources and getting us nowhere.
Exactly. But a compiler can never be completely sure it's identified every possible infinite loop because of the halting problem. It might look at a piece of code and think, oh, this will definitely stop, but in reality, under certain conditions, it could turn out to loop forever.
So that must be a real headache for people who write compilers. How do they actually deal with that limitation?
Well, they have to get pretty clever. Instead of trying to solve the halting problem directly, they use these things called heuristics.
Heuristics?
Yeah, they're basically like rules of thumb that help them identify likely infinite loops. They also use static analysis, which means analyzing code without actually running it to try and catch potential problems.
So it's like they're making the most educated guesses they can, since they can never be absolutely sure.
That's a good way to put it. It's this constant balancing act between, optimizing the code as much as possible and the risk of introducing some kind of error.
Okay, so compilers have to work around the halting problem. What about antivirus software? We touched on how it's impacted, but how do cybersecurity experts actually tackle this challenge?
Well, it's tricky. Antivirus software tries to analyze code to see if it shows any malicious behavior. But, like we talked about before, definitively proving that a program will eventually do something harmful is directly related to the halting problem.
Because it's like trying to predict the future behavior of a program, right?
Exactly. You would have to show that the program will halt at a very specific point where it carries out that malicious action, and we know we can't always do that.
So how do antivirus programs even work if they can't be 100% sure about what a program's going to do?
They have to take a multi-pronged approach.
Okay.
They use signature-based detection, which is looking for known patterns of malicious code. They also use those heuristics we talked about to identify any suspicious behavior, like a program trying to access files it shouldn't.
Yeah.
And they use sandboxing techniques to run suspicious programs in isolated environments where they can't actually cause any harm.
So it sounds like instead of solving the halting problem, they're using this combination of strategies to do their best to catch the malware.
Exactly. And it's an ongoing arms race as the people who create malware are constantly finding new ways to evade detection.
Wow. This is getting more and more complex. It seems like this halting problem touches so many different areas of computing. So we talked about compilers and cybersecurity, but
Yeah.
I remember you mentioned software testing too.
Ah, yes. Software testing. That's another area where the halting problem really shows up. Imagine you're a software developer and you've just made a bunch of changes to a program. You want to make sure your code still works as expected.
Of course, you don't want to break anything.
Exactly. And one way to test this is to see if your modified program halts on the same inputs as the original code. But again, because of the halting problem, we can't always be certain about this.
So how do developers make sure their changes haven't introduced some hidden bug that might cause the program to just freeze up in some unexpected situation?
Well, it all comes down to managing risk. They can't rely on a perfect solution, so they focus on thorough testing. Running the program on a wide range of inputs, including those edge cases and unusual scenarios, to try and uncover any potential for those infinite loops.
So it sounds like developers are constantly battling this uncertainty that the halting problem introduces.
In a way, yes. They have to adopt strategies that mitigate the risk, even though they can't completely eliminate it. And this brings us to a deeper realization about the halting problem. It's not just a specific problem to be solved. It's more like this fundamental principle that shapes our understanding of what's actually possible when it comes to computation.
This has really been eye-opening. We've seen how this seemingly abstract concept has practical implications in so many different areas.
And we've only just scratched the surface. There's a whole world of fascinating concepts related to the halting problem.
Like what?
Well, we've been talking about the standard halting problem, but what if we ask whether a program halts on every possible input, not just one specific one? Well, that's the universal halting problem.
So instead of asking, will this program eventually stop for this one task, we're asking, is it inherently, well-behaved for any task we could possibly give it?
Exactly. And then there's this really intriguing case of lossy computation, where information might be lost during a program's execution. Turns out that in certain models of this lossy computation, the halting problem actually becomes solvable.
Wait, really? How can introducing uncertainty make an unsolvable problem solvable? That sounds like a paradox in itself.
It does, doesn't it? But that's kind of the beauty of this whole field of theoretical computer science. It challenges our intuitions and often reveals these surprising truths about the nature of computation.
Okay, my mind is officially blown. So we've got this universal halting problem that's even harder to solve than the regular one. And then we've got this lossy computation that somehow makes it solvable. What else is there?
There's one more fascinating twist we need to talk about. Imagine a machine. Let's call it an oracle machine. It can magically solve the halting problem for other machines.
Okay, so like a super intelligent machine that can look at any other machine and just instantly know if it will halt or not.
Right. But can this oracle machine figure out its own fate?
That's a good question.
And the answer is a resounding no. Even a machine with this almost magical ability to solve the halting problem for others still can't determine if it itself will ever halt.
Wow. So even with this incredible power, it's still bound by the same fundamental limitations.
Exactly. It's this really profound reminder that the halting problem is not just a puzzle to solve. It's this fundamental truth about the limits of computation. And it's a truth that has far-reaching implications that go even beyond the world of computers.
What do you mean by that?
Well, let's consider this. If the halting problem highlights the limits of what computers can do, what does that say about the limits of our minds? Can we as humans solve problems that are fundamentally unsolvable for a machine?
Whoa. That is a deep question. I don't know if I have an answer for that one.
And that is a perfect place to leave off for now.
Yep.
We've really gone deep on this. We've talked about the logic of the halting problem, its real-world impacts, and even touched on those philosophical implications. But there's still so much more to unpack.
I'm ready for more. Where do we go from here?
Let's delve even further into these mind-bending variations on the halting problem next time.
We've been on quite a journey with this whole halting problem thing. It's amazing how a question about whether a program will ever stop can lead us to, such profound insights about the nature of computation and software and maybe even about ourselves.
It really stretches the imagination. So before we wrap up, let's do a quick recap of what we've learned.
Sounds good.
Okay. So the halting problem essentially asks, can you create a program that can analyze any other program and determine if it will eventually stop or run forever? We've been calling it the halting oracle, right?
Right.
And as we've seen, the answer is a resounding no. This halting oracle can't exist. The halting problem is fundamentally undecidable.
Right. And we even talked about a couple of different ways to prove this, like that proof by contradiction, where we imagine a program that defies the predictions of our, hypothetical halting machine.
Exactly. We also discussed how this seemingly theoretical problem has very real-world consequences. Things like compiler optimization, cybersecurity, even the task of just testing software. It creates these limitations and uncertainties that programmers have to deal with all the time.
And then we went even deeper and explored those Turing machines, those theoretical models of computation.
Yeah.
They helped us see why the halting problem is undecidable, not just for one type of computer, but for any system that can do computation.
Right. And we even got a glimpse of some of the weirder variations of the halting problem, like the universal halting problem, where we ask if a program will stop for any possible input, not just a specific one.
Right. And then there's that strange case with the lossy computation, where introducing randomness and data loss somehow makes the halting problem solvable.
Yeah, that one's a head-scratcher for sure.
And of course, we can't forget those oracle machines that can somehow solve the halting problem for other machines, but not for themselves.
A lot to think about.
Yeah, it's been quite a ride through the world of theoretical computer science.
It has. But I think the most intriguing question we've touched on is this. Do the limitations that the halting problem highlights tell us anything about the limits of our own minds?
Yeah, that's the question that really got me thinking. If computers with all their processing power hit a wall with the halting problem, does that mean we as humans are stuck with similar limits? Or is there something about human thought that allows us to break through?
That's the question that philosophers and computer scientists have been debating for decades. And it gets at the heart of what it means to be intelligent.
So what do you think? Are our minds just super advanced computers subject to the same rules and limits? Or is there something more to consciousness that lets us think outside of those computational boxes?
Well, it's tempting to compare the brain to a computer. I mean, we do process information, we store memories, we make decisions. It's a lot like a machine running a program. But I think there's a fundamental difference.
Oh, what do you mean?
Well, computers operate within these really strict formal systems. They excel at following rules and doing logical operations, but they struggle with ambiguity, nuance, and those creative leaps that really characterize human thought.
So you're saying that while our brains can do logical processing, we also have this ability to make intuitive jumps, see connections a computer might miss, even come up with completely new ways to think about a problem.
Exactly. We can imagine, we can create, we can even change the rules. We can step outside of those formal systems that kind of trap computers.
This reminds me of those aha moments when a solution just pops into your head. It feels like more than just a bunch of logical steps.
Yeah.
It does, doesn't it? And that's the real challenge in understanding consciousness. It's not just about raw processing power or the ability to follow an algorithm. It's this ability to think in ways we don't even fully grasp yet, let alone replicate in a machine.
So maybe the halting problem shows the limits of computation, but it doesn't necessarily limit human thought.
Yeah, that's a great point. It's a powerful reminder that there are definitely limits to what we can compute, but it also opens up a space for wonder and possibility.
Makes you wonder what other seemingly impossible problems we could solve if we tap into the full potential of, human ingenuity and creativity.
Absolutely. That's what keeps this whole field so fascinating. We're constantly pushing the boundaries of what we know and what we think might be possible.
This has been an amazing deep dive. I feel like I have a whole new understanding of the power and the limits of computing.
It's been a pleasure exploring all of this with you. And to all our listeners out there, keep questioning, keep exploring, keep pushing those boundaries of your understanding. Because even though we can't solve every problem, the journey of exploration makes it all worthwhile.
Until next time, keep diving deep.